So now we are going to discuss about the telescope, in which we have two cases. This is the first case of LDDV, in which the final image is formed at a distance of 25 centimeter from the eyepiece. Okay, so now we are going to draw the diagram and then we will find the magnifying power. So here we have this. I draw the line. Now the rays are coming from the infinity. The rays are coming from the infinity. Okay, so since object is placed at infinity, so rays are coming from the infinity. Keep this thing in mind. And now we are drawing the more rays. We're drawing the more rays. This is the another ray that is coming from the infinity, and it will go like this because it is a converging lens. So it will converge the light ray. This. So that's how we got. That's how we got the image of the object over here. This is the image of the object, E dash B dash. Keep in mind, object is placed at infinity and we got the image. These rays are coming like this, and these rays are exactly parallel because they're coming from infinity. Okay, now since the rays are coming from infinity, the image should be formed at focus. So it should be the focus of the objective lens. Keep in mind, A dash and FO are the same point. Here we have another focus, like this is FO dash. Now this is the FE. Keep in mind, this is FE dash, and over here we have FE. These are different focuses. Now we draw the virtual line which is passing through the optical center. So that line is passing through the optical center. And now we are converging these two rays because this is the converging lens. So rays should be converged like this. Now when we draw these rays backwards, drawing these rays backwards, now these all the three rays are intersecting at this point. So when we draw these backwards, we got the point of intersection. And at this point, what we have the image. And that is the final image. A double dash, B double dash. This is the final image. Now, we have to make the optical center of the two lenses. This is O and this is E. And now by using geometry, we can solve this figure. We can solve. Now keep in mind one thing. The image made by the objective lens is the object for the eye lens. Keep in mind. Okay. So the image made by the objective lens works as the object for the eye lens. Okay. So A dash B dash is the object for the eye lens, and A dash B dash has been magnified by the eye lens as A double dash B double dash. Now the angle made by object is known as alpha, and angle made by image is known as beta. Keep this thing in mind. Now if this is alpha, so this should be also alpha because vertically opposite angle, alpha and alpha. And now you have to find the value of tan alpha and tan beta. So I'm finding the value of tan alpha first. Tan alpha is how much? Tan alpha, that is equals to perpendicular upon base. Base is OA dash. And since alpha is a very small angle, so you can take tan alpha as alpha. In the same manner, we can find tan beta, that is perpendicular upon base, which is EA dash, and it should be equivalent to beta because angle is very small. We can take tan beta as beta. Now if you want to find the magnification of this combination, we know that we have formula like this, writing in the corner. You can write here also. This. Now we're writing in the corner. What we have here, M is equals to magnifying power is equals to angle made by image divided by angle made by object. Put the values. What we got? We got A dash B dash divided by EA dash, and then we have A dash B dash divided by OA dash. This should be cancelled out. We left with OA dash divided by EA dash. So that's how we got the magnifying power. Okay. Now you can put the values of OA dash and E dash. So let's make some like notations. This should be the distance of the image. This should be plus VO, or you can write also plus FO because that is also the focal length. And this should be minus UE because this is the distance of the object from the eyepiece. And this, of course, we know that this is minus D, the distance of the image from the eye lens, minus D. And now we can put these values in the equation. So we got OA, that is plus FO, divided by minus UE. So we got the equation 1. This is called equation number 1. And now you can solve the eye lens. Keep in mind this is called eye lens. This is called eye lens because we observe from here, like this is the location of the eye. So we observe the image from this point. So that's why it is called eye lens. Okay. Now what we have to do, we need to first, I'm going to clean up. Now, okay. So now what we are going to here, we're going to here solve the condition for the eye lens. Okay. So I'm solving for the I lens. For I lens, what we have? I lens 1 by f is equals to 1 by v minus 1 by u. This is the lens formula. And we can just put the values. Now we're putting the values. F is plus fe. V is how much? Minus d. And u is how much? Minus ue. Now we put these values. We can put these values. So we got 1 by fe plus fe. Then we have 1 by minus d minus 1 by minus ue. And now 1 by fe plus 1 by d is equals to 1 by ue. Now what we can do, we can put these values in the equation 1. So putting 1 by ue in equation 1, what we got, m is equals to minus fo into 1 by ue. So you need to put this value over here. You need to put this value. So what we got this thing, 1 by fe plus 1 by d. And now when you take 1 by fe as a common, so we got fo by fe. That should be plus 1 by d. So this is the expression of the magnifying power.